So the atomic theory, the idea that all matter is composed of atoms, came out of observations and laws, specifically the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So what are those? The law of conservation of mass says in a chemical reaction, matter is neither created nor destroyed. And this came about from the work that Antoine Lavoisier did. We talked about him in the first chapter. So when a chemical reaction occurs, the total mass of substances doesn't change. Because what's happening is the particles are just rearranging. So you can imagine, taking a Lego thing, maybe it's a spaceship or something, and you could weigh it on a balance and see how much it weighs. And then you take that apart however you want, and you use all the pieces, you don't have leftover pieces, and you weigh that again. Is it going to weigh different than it did before because you rearranged the pieces? No, it's going to weigh the same. We can use this to do some very simple calculations. Here, if you react 7.7 grams of sodium, 11.9 grams of chlorine, and they make sodium chloride, the mass of sodium chloride produced is equal to the sum of the masses that you started out with. So there's a couple questions on the worksheet that talk about law of conservation of mass, and those are just adding, subtracting problems. We're not doing stoichiometry yet, because if I haven't talked about it in class yet, we're going to figure you don't know about it yet. We should be able to answer a question like this. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? A, the matter that composed the log reacts to form gases that are released into the air. B, the matter that composed the log is converted into energy. C, the matter that composed the log is still present in the ashes but has a much lower mass. So just general strategy on multiple choice questions. Always read all the choices. And then sometimes the correct choice doesn't jump out at you, but you may be able to identify a choice that's wrong. Can you pick one of these that's wrong? B is wrong. Because this says that matter is converted into energy. But the law of conservation of mass says matter can't be created or destroyed. You have to have the same amount of matter afterwards. So that's not true. So now we're 50-50 guessing, right? Let's look at this one. So the matter that composed the log is still there, but its mass is lower. Is that possible? No, it's not. A is the correct answer. So what happens when wood burns, wood has a lot of carbon and hydrogen in it, those elements combine with the oxygen from the air and create carbon dioxide and water. And those are gases because it's hot. And they float away and you don't see them, right? So it's not at all obvious. It looks like matter's disappearing, but it's not. Anybody have any questions about that? That's why Lavoisier had to do his experiments in a closed container. If it was in an open container, then the mass did seem to change. Definite proportions. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So if you decompose water, let's see, 18 grams of water, you'll get 16 grams of oxygen and 2 grams of hydrogen. And so we can look at that ratio. As a ratio of 16 to 2, we could just report that as a number, 8.0, or as a ratio 8 to 1. So all water, no matter where it comes from, has this mass ratio of 8 to 1. The mass ratio of nitrogen and hydrogen, nitrogen to hydrogen in ammonia, is 4.7 to 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? Well, this is really not about doing a calculation, but 4.7 grams of nitrogen to 1 gram of hydrogen. That's an H. And so we're looking at a sample that has 10 grams. The ratio has to be the same. This one has 10 grams of hydrogen. How much bigger is this than that? 10 times. So if there's 10 times as much hydrogen, there has to be 10 times as much of the nitrogen. So what's the correct answer? D. It'd be 47. Two samples of carbon monoxide are decomposed. One produces 17.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. The law of definite proportions says what about the ratios for these two different samples? Are they going to be the same or different? They're going to be the same. So we need to show that they are the same ratio. And that's not how you do it. So this first one was 17.2 grams of oxygen to 12.9 grams of carbon. And so we could do the math there. And my calculator shows me 1.33333 for error. But quick review of sig figs, both of these have 3 significant figures, and so my answer should have 3 significant figures, and so that ratio is 1.33. Then we look at the other sample, 10.5 grams of oxygen to 7.88 grams of carbon. 10.5 divided by 7.88. The calculator is saying 1.33248 goes, just kind of runs on. This one also, 3 sig figs. We're counting sig figs when we're dividing, so this should have 3 significant figures. 1.33. This does support the law of definite proportions. There's a question kind of like this on the worksheet too. The law of multiple proportions. This one is so confusing when you say it in words. When 2 elements, just call them A and B, form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. The reason for that is, because we have atoms, you can have with 1 atom of A, you can have 1 atom of B, or 2 atoms of B, or 3 atoms of B. You can't have 2.5 atoms. And so the ratios end up being whole numbers because these are combining in a way where you only have whole numbers. So let's look at this example. Let's look at this example. So carbon monoxide, carbon dioxide. Both compounds containing only carbon and oxygen. Carbon dioxide, 1 carbon, 2 oxygens. Carbon monoxide, 1 carbon, 1 oxygen. So if we look at the ratios like we were doing for law of definite proportions, we find that this is a ratio of 2.67 grams of oxygen to 1 gram of carbon. So 2.67 to 1, and this one is 1.33 to 1. So what the law of multiple proportions is saying is if you look at those mass ratios and you take the ratio of the ratios, right? If we want to get a whole number, we have to take the big number and divide it by the small number. If we take the bigger ratio and divide by the smaller one, we get a whole number every time. And it seems like almost magic, but it's because of this, they understood the particulate nature of matter. So here's an example using that idea. Hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 1.125 grams of hydrogen to every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 625 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So with the definite proportions, we were talking about two different samples of the same compound. And if we look at the ratio of the masses of elements, they were the same, right? Here, we have two different compounds. Are those ratios going to be the same? No. They're going to be different. And what's even more strange is that if we take the ratio of the ratios, we should get a whole number. So let's do this one. So for the water, we've got 0.125 grams of hydrogen per 1 gram of oxygen. And I'm just going to call it HP, for the hydrogen peroxide, 0.0625 grams of hydrogen to 1 gram of oxygen. So this is a ratio of 0.125, and this is a ratio of 0.0625. They are different. These are different compounds. To demonstrate the law of multiple proportions, I'm going to take the bigger ratio and divide by the smaller one. And I get 2. Yeah.
So they have to be the same elements in the multiple?
Yes. Yeah, for the multiple proportions, you have to be talking about compounds containing the same elements. Yeah.
What is the purpose of this, of the law of multiple?
What is the purpose of it?
Yeah.
That's an excellent question. I kind of ask myself that sometimes.
Yeah, the other
'Cause
one makes sense.
why do you really need to know this?
Yeah.
I think
Like
it's
when-
mostly because this was part of the evidence that
Oh, okay.
matter
So
is
the
composed of
atoms.
atoms.
Oh,
Yeah. If you don't understand the law of multiple proportions, you can still get an A in Chem 1A, okay? Maybe in the future this will be a watch this video on your own section. This is a little more important. Dalton's atomic theory. So these are the ideas. I'm not going to ever make you write these out. But we should understand this idea. So each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. So today we've got a lot of technology, and everything everyone has studied all agrees that atoms are real, even though nobody has seen one, right? Is everything here completely true?
Is anything ever true?
So we'll find out today that number 2 is not quite correct. And
Number 1 is entirely correct. Atoms can be destroyed.
yeah, so atoms can be destroyed. You've heard of atom smashing, right? So you can bombard atoms and split them. It's called fission. It's a nuclear reaction, right? So here, what we're saying, we added something in, to preserve the truth here, in a chemical reaction, atoms only change the way that they are bound together. In a nuclear reaction, one element can change into another element. But we don't do that in Chem 1A. Atoms are not indestructible. So does that mean this atomic theory just is thrown out the window? No, we're not gonna throw the baby out with the bathwater. We're just gonna throw out the bathwater, right, and keep the baby. I don't know why I used that one. So we modify this, like this is a modification, adding in a chemical reaction. Now it makes that statement true.